Hello viewers, I am Kausalya. Today we are going to solve problem number 5 under the topic state space model. The problem is construct the state model of the mechanical system shown in figure. So this is the given mechanical system, right? So tell me whether this is a translational system or a rotational system. Here this is a translational system because the displacements are given here, you see, in terms of y1 and y2 are not in terms of theta, right? So this is a mechanical translational system, right? As usual, again we have to refresh our chapter number 1. Again we have to go back to our previous chapters. That is, we have to draw the free body diagram, right? Which is followed by force balance equations, right? So first let me start with mass m1. So as usual, you see, to this mass m1 f of t is a direct applied force, right? Due to this applied force there will be opposing forces which is produced by these elements which is connected to m1, right? So simply we can say that just count the number of elements which are attached to mass m1. So you see how many things are connected with m1? 1, 2, 3, right? Apart from that, an opposing force will be also produced by m1. So totally the forces acting on m1 is equal to 4, right? So now we will draw our free body diagram, right? So here this is our mass m1, right? To this mass m1 there is an applied force which is f of t, and there are opposing forces, right? 3 opposing forces, because you see again when you look back, an opposing force will be produced by k1, b1 as well as by this m1 also. So here I had drawn 3 opposing forces and 1 applied force, right? And the direction should be opposite to each other, okay? Make a note of it. And the respective displacement due to this force f of t is y1, right? Now we are going to write expression for each and every term. So this fm1 is nothing but m1 into d square y1 by dt square, that is acceleration here. And next thing is fb1, and this fb1 is given as, again when you look back, you see this b1 is connected between m1 as well as m2, right? So while writing expression, since we are considering m1, this y1 should be given priority. So while writing expression, you see here it is written as b1 into d by dt of y1 minus y2, right? Because here we are considering m1, therefore y1 should be written first. So y1 minus y2. Likewise, again you see this fk1, that is this k1 is also common for m1 and m2. So while writing expression, it is written as k1 into y1 minus y2, right? Now, by Newton's second law, we are writing the force balance equation at node M1. So here, this is your applied force and these are the opposing forces. So write an expression. So f of t is equal to fm1 plus fb1 plus fk1, right? So now substitute the respective expressions. So f of t is given by fm1 is, we know, right? We are having expression this one, okay? So write this expression over here. Similarly for fv1 and fk1. The next step is we are going to simplify this expression, right? So here you see I'm going to multiply these terms. So what happens? b1 into d by dt of, that is this y1, right? So b1 into dy1 by dt. Again here I am having minus, so minus into b1 into dy2 by dt plus k1 y1 minus k1 y2, right? Name it as equation number 1. So next consider m2. So again to this m2, so this is our m2, right? Just count the number of elements which are connected to m2. So 1, 2, 3, 4, right? So totally 4 elements are connected, and how many number of forces will be present? Totally 5 forces will be present, right? Apart from these 4 elements, another force will be created by our mass m2. So these are the 5 opposing forces and the respective displacement is given as y2, right? So write down the expression as usual, the same thing. So fm2 is given as m2 into d square y2 by dt square, And again for b2 is given as b2 into dy2 by dt. And again fb1 is given as, since it is connected between m1 and m2, right? Here we are considering m2, so the respective displacement of m2 is y2. So we have to write y2 first. So b1 into d by dt of y2 minus y1. And next fk2 is given by k2 into y2. And finally fk1 is given by k1 into y2 minus y1. Again it is connected between our m1 and m2, right? Now we are going to apply Newton's second law. So by Newton's second law, applied force is equal to opposing force here. But here you see, when you look at this diagram, we don't have any applied force, right? We are having only opposing forces. So just write down the expression, right? You see, opposing forces equal to 0. Now substitute the respective expressions here. So when you substitute the expressions, right, again we have to multiply. So here you see this term here as such, and here also this term remains the same. And here when you multiply b1 into dy2 by dt minus b1 into dy1 by dt, and again the remaining terms k2 y2 plus k1 y2 minus k1 y1 equal to 0, right? So mark this as equation number 2 here, right? Now we are going to select our state variables based upon these two equations 1 and 2. So we know that, right? Initially we will start with our displacement, right? We are having two outputs, that is two displacements y1 and y2. So x1 is equal to y1 and x2 is equal to y2. Again in our expressions we are having differentiated terms, right? So dy1 by dt we are taking it as x3, and again dy2 by dt we are taking it as x4. And again that is a double differentiation also, right? This is a single differentiation, again it is differentiated here. So when you differentiate this term again, we will be having expression like this, d square y1 by dt square. So in order to represent the differentiation, here a dot is kept over x3, right? Likewise in x4 also, again we are, this dy2 by dt is differentiated one more time. So the expression is d square y2 by dt square. Since this term is differentiated, here it is represented as x4 dot here, right? Am I making the things clear? We are having two displacement y1 and y2 which is given in the problem. So initially we are taking these two values as x1 and x2, right? Since in expressions 1 and 2 we are having both differentiated terms and double differentiated terms. So again this differentiated terms I am taking it as x3, right? And here this dy2 by dt as x4, right? So here even you may ask the question, dy1 by dt can be written as x1 dot, right? We can also write like this, but when this happens we won't get a proper final output equation, because when we equate this dy1 by dt equal to x1 dot, and here this d square 1 by dt square should be written as x1 double dot, which is not in our state space representation format, right? So only we are briefing like this. Again we are going to substitute these values in our equations 1 and 2, right? So you see this is our equation number 1, right? So here and I forgot to say this f of t, this is our input force, right? So this f of t should be always considered as u here, right? So f of t is represented as u, and m1 into this d square y1 by dt square, it is nothing but x3 dot. So here it is written here, plus b1, this d by 1 by dt is nothing but x3, right? So write x3, and d by 2 by dt it is x4. So replace it with, here it is x4, right? And plus this k1 y1 is nothing but x1 and y2 is nothing but x2, right? So here now we are going to frame an expression in terms of x3 dot, right? So we are going to rearrange the terms accordingly. So since we need m1 x3 dot, I am keeping this term as such here, and I am going to shift these terms to the left hand side. Whenever we shift these terms to the left hand side, that is there will be a sign change, right? Plus will become minus and minus will become plus. This is the thing which happened here. And the next step is I want only x3 dot. So I am moving this m1 to the left hand side. Here it is in the numerator part. When you move to this side, this m1 occupies the denominator part, right? So here this is our expression. Again we are rearranging, right, in the form of that is x1, x2, x3 and x4. Just here the above expression is rearranged here. You see, minus k1 by m1 x1, right? Next plus k1 by m1 x2 here. And next x3 is here. So minus b1 by m1 x3 plus b1 by m1 x4 plus u by m1, right? And again we are doing the same thing in equation number 2. So again substitute the values. You see, d square y2 by dt square is x4 dot and dy 2 by dt is x4. Likewise, you just replace the values, right? And here again we are having x4 dot. So we need only x4 dot, right? So I am moving the remaining terms to the right hand side. So again there is a sign change over here. And finally you see, here I am having x4 term common, that is minus x4 is common. So when I take minus x4, the remaining terms are b2 plus b1. And again here plus b1 x3. And again minus when x2 is commonly taken outside, then k1 plus k2. And here plus k1 x1, right? Again I need only x4 dot. So I am moving this m2 to the right hand side. So this occupies the denominator position, right? So this is our expression for x4 dot. So next we are moving to our first, that is first we had assigned, right? We have taken this expression in state variable, that is x1 is equal to y1. So we need x1 dot, right? So we are differentiating with respect to dt. So when you differentiate, this dx1 by dt is nothing but x1 dot and d1 by dt is x3, right? We already have this expression. So just substitute here and finally we are having x1 dot equal to x3. Likewise again x2 is equal to y2. So again differentiate and finally we are having an expression as x2 dot is equal to x4 here, right? So finally we had framed expressions for x1 dot, x2 dot, x3 dot and x4 dot also. So we are writing it together here. You see, these are the expressions. Now we are going to rewrite it in the form of matrix, right? So here you see, when you arrange it in the form of matrix, again we are having these four values, x1 dot, x2 dot, x3 dot and x4 dot. And when you have here the four values, then the respective values here are x1, x2, x3 and x4, right? So again you see the value of x1 dot is x3, right? What it means, there are no x1 term, x2 term as well as x4 term also. So we are writing it as 0 here. You see 0, 0, that is no x1, no x2 and I am having x3. So its coefficient is 1 and x4 is also 0, right? And similarly for x2 dot, only x4 is present. No x1, x2, x3. Therefore 0, 0, 0, 1 here. And again in x3 dot and x4 dot we are having values. Coefficient of this x1 is minus k1 by m1. x2 is k1 by m1 and finally x3 is minus b1 by m1 and x4 is b1 by m1, right? And again similarly for this final expression, you see x1 k1 by m1 and for this x2, okay, for x2 the coefficient is minus k1 plus k2 by m2 and here x3 b1 by m2 and here minus b1 plus b2 by m2, right? So apart from this, we are having an expression here, you see 1 by m1 of u, that is this is our input voltage, here it is input force, right? So how to represent it here, again we are having a u matrix, right? So represent the u matrix here. And again in x1 dot and x2 dot there are no u terms, so write it as 0, 0. And in x3 dot we are having 1 by m1, right? So write it 1 by m1 and again in x4 dot also there is no u term, so it is 0, right? So just name it as our equation number C. Let the displacements, that is y1 and y2 are the displacement, right? Due to this given force F of t, we are having these two displacement, right? In masses m1 and m2 respectively. So here again, y1 is x1 and y2 is x2, right? These are all the things we had already considered. So we have to write output equation. So how to write an output expression? You see, output should be in terms of the respective state variables. So we are having two outputs, that is two displacement y1, y2, right? And how many state variables do we have? We have four state variables, right? So here write them respectively, x1, x2, x3 and x4. Right. So while writing expression, you see, for the coefficient of x1 is 1. So it is written here. Here there are no x2, x3 and x4 terms. So it is simply 0. Right. Again, when you move to y2 equal to x2, here there is only x2 term. No x1, x3 as well as x4. So the values are 0 and here I had written 1. Right. So mark it as equation number D. So this equation C and D together forms the state model of the system. Right. Here comes the end of the problem. If you have any doubt, let me know in the comment section. Thank you.